Good day, everyone. Today we will discuss a topic related to soil chemical properties, which is all about the soil colloid. So, what is soil colloid? A colloid is a substance microscopically dispersed throughout another substance and have a diameter of between approximately 1 and 1000 nanometers, and it usually consists of the humus and the clay. So we have two kinds of soil colloids. We have the humus and we have the clay. So there are different types of soil colloids. If we discuss it specifically, we have the inorganic colloids, or those that are called clay. Under the inorganic colloids, you have the crystalline. Under the crystalline, we have crystalline silicate and crystalline non-silicate. Under the inorganic colloids, we also have the amorphous, or the non-crystalline one. Under the amorphous, we have the amorphous silicate and the amorphous non-silicate. And we have also what we call the organic colloids, or the humus. So we have two general types, the inorganic and the organic colloids, or clay and humus respectively. And under the inorganic colloids, we have the crystalline and amorphous. Under the crystalline, we have the crystalline silicate and crystalline non-silicate. Under amorphous, we have the amorphous silicate and amorphous non-silicate. Most clay minerals are aluminosilicates, where the major elements in their structure are the following: 47% silicon, 27% oxygen, and 8% aluminum. And these three are the most abundant element in the Earth's crust. Now let us discuss the inorganic, or the clay colloids. Under the clay colloids, we have the crystalline, and crystalline is consists of atoms that are in definite order, that repeats extensively in three dimensions, while the other one, which is amorphous, do not have a definite long-range atomic pattern. The atomic arrangement and composition of those influence on the properties of the clay colloids. Let me give you an example. Diamond and graphite have the same atomic composition but different arrangement, and because of that, these two will have different properties. While potassium chloride and sodium chloride have exactly similar atomic arrangement but different composition, and because of that, these two will have different properties. These are the carbon atoms of diamond that are arranged tetrahedrally, and each carbon atom is attached to four other carbon atoms. If we take a look on the carbon atoms in graphite, they are also arranged in an infinite array but are layered. And because of these different arrangements, they will have different properties. So let's take a look on the crystalline silicate clays. So these crystalline silicate clays are composed of sheet-structured aluminosilicates and have various types depending on the ratio of silica sheet to alumina sheet in a crystal structure. And each type does not occur in pure form in a clay fraction of soil, but there is an intimate mixture of different clay minerals in a given soil. So this is an example of a soil showing its different crystalline silicate clays under the microscope. You can see that there is what they call Kaolinite or Kaolinite, the illite or the Smectite. So in a given soil, it may have a lot or one or two or more than three crystalline silicate clays. And this shows that each clay type does not occur in pure form in the clay fraction of the soil. Now, the crystalline silicate clays have 5 groups. So let's discuss those 5 groups one by one. We have the first type, which is the candites. Candites have one silicon sheet or tetrahedral sheet and one aluminum octahedral sheet. They belong to the 1:1 type silicate crystalline silicate clay. And candites are the simplest of the silicate clay mineral groups. They are non-expanding. They do not expand when wet. The interlayer between the 1:1 sheets is closed so that little water and few cations can enter between the sheets. And kaolinite is the most prominent member of this group. Other examples include halloysite, anoxide, and dikite. So this is the structure of a tetrahedron, particularly the silica tetrahedron. A tetrahedron may consist of a central cation. It can be silica ions or aluminum ions ion rather, that is surrounded by 4 oxygens. And this one is an aluminum octahedron. Aluminum octahedron is consists of aluminum central cation surrounded by oxygens. Or it can be hydroxyls. The central cation could also be iron or magnesium ion. This is the structure of the 1:1 clay type or kaolinite. It has one octahedral sheet and one tetrahedral sheet. That is why it is called 1:1 clay type. This is kaolinite under a microscope. Kaolinite is a good rose. So in these photos, you can see a kaolinite mine area in Bulgaria. So that is kaolinite. So we are now done with the candites. Now we move to the next group. We have the smectites. Smectites have one aluminum octahedral sandwiched between two silicon tetrahedral sheets. So they belong to 2:1 expanding type of clay. And montmorillonite is the most important member of this group. A soil that has montmorillonite is the dominant clay, shrinks when dry, and swells when wet as water leaves or enter the interlayer space. Other examples include natronite, saponite, hectonite, and sauconite. So this is the structure of the 2:1 clay type montmorillonite. We have two tetrahedral sheets sandwiching the octahedral sheet. And there is the interlayer space that can be entered by water. So this type of clay, when wet, can expand, and when dry, can shrink. Water can move into the clay structure of the 2:1 clay minerals, causing them to expand. So this is montmorillonite under the microscope. The next one, or the next group we have is the Vermiculite. This one is also a 2:1 clay type, but compared to Smectites, this has limited expansion. There is considerable substitution of aluminum for silicon in the tetrahedral layer of vermiculites, which accounts for most of the very high net negative charge. The amount of water and the kinds of cations in the interlayer are more limited than in smectites. Hence, expansion is less. Another group is the illite. This is also a 2:1 type of clay, which is non-expanding. So remember, we have the 2:1 expanding type, which is the smectite or montmorillonite, the most dominant or the prominent example, and the smectites. We have the limited expanding 2:1 clay type, which is the vermiculite. And now we have the non-expanding type 2:1 clay, that is illite. Illite is sometimes referred to as hydrous mica because it is believed to be the weathering product of mica. The presence of potassium ion in the interlayer, which acts as a binding agent, contributes to the stability and non-expanding nature of the illite. So this is illite under the microscope. Illite or fine-grained mica. The last one we have is the chlorite. Chlorite is a 2:1 non-expanding type of clay. The additional layer is a magnesium hydroxide or a brucite sheet in the interlayer space between the 2:1 sheets. And it has relatively little water adsorption between the chloride crystal units, which accounts for the relatively non-expanding nature of this type of clay. Now, in comparison, these are the structures of those 5 crystalline silicate clays. For kaolinite, you have one octahedral and one tetrahedral sheet. That is why it is called 1:1 non-expanding or no swelling clay type. For smectite, the example is montmorillonite. You have two tetrahedral sheets sandwiching one octahedral sheet. And this smectite is an expanding clay type where water can enter on the interlayer space, expand when wet, and shrink when dry. Vermiculite, just like smectite, is also 2:1 with limited expansion because of the magnesium cation present in the interlayer space, which acts as relatively binding agent. For the fine-grained mica or illite, this is also 2:1 non-expanding type because of the potassium cations present in the interlayer space. And the last one we have is the chlorite, the 2:1 silicate clay. This has hydroxide sheet on its interlayer space. The next one we have is the amorphous silicate clay. So now we are finished with the crystalline silicate clays. Now we are on the amorphous silicate clay. Amorphous silicate clays are usually associated with relatively young soils derived from volcanic ash and characteristically containing high organic matter. And it is represented by allophane and immobile. Exhibit very low degree of stickiness And by the way, amorphous means without shape. It doesn't have a definite pattern, just like the crystalline silicate clay. For example, olefin is thought to be a gel or jelly-like in soils to poorly crystalline detection, hence difficult to know how it exactly looks like. We also have the amorphous non-silicate clays. And this type of clays occur as amorphous hydrous oxides of iron and aluminum. Hydrous oxides of iron and aluminum are also called Sesky oxides. And this type of clay is especially important in the more weathered soils of warm and humid regions such as the ultisols and oxysols. By the way, ultisols and oxysols are two of the 12 soil orders, and those 12 orders will be discussed on my next videos. The type of clay is relatively low in plasticity and stickiness, and net charge ranges from slightly negative to moderately positive. Examples of this are the gibbsite, the hematite, and goethite. This type of clays are very stable and persist indefinitely. Most common colors are yellow, red, and brown. They are highly weathered, so no more nutrients to be released during weathering. So this is a structure of gibbsite or aluminum hydroxide. So we are now finished with the inorganic colloids. Now we're moving on with the organic colloids or the humus. These are some of the attributes of these organic colloids. They are high in molecular weight, highly charged, has a large surface area per unit mass, and these attributes make the humus very reactive in soils. Other attributes include the colloidal soil organic matter decomposes slowly and colors soils brown or black. So organic colloids are actually the ones responsible for the brown or black color of soils. And both the product that is synthesized or created by microorganisms and the product of breakdown or decomposition of other organic compounds. So organic colloids is in a dynamic state and always changing, and this type of colloid is not as stable as the clay colloids. Organic colloids is basically composed of carbon, hydrogen, and oxygen. The cation exchange capacity of humus per unit weight far exceeds even that of Montmorillonite. So take note of that. The nutrient holding capacity of the humus or the cation exchange capacity exceeds that of Montmorillonite. And constituents of this are the following: the fulvic acid, the humic acid, and the humine. So these three will be discussed on another topic in one of my videos also. So this is a simplified diagram showing the principal chemical groups responsible for the high amount of negative charge on humus colloids. The three groups can lose their hydrogen ion by dissociation and thus become negatively charged. So as you can see, those groups are the carboxylic group, the phenolic hydroxyl group, and the alcoholic hydroxyl group. This one is humic acid under the microscope. For the properties imparted to soils by colloids, for chemical, that is the sources of ions for plant nutrition, and also source of electronegativity or cation exchange capacity, and also buffering capacity. For physical, the large surface area per unit of mass and the plasticity. Now let's move on to the general properties of soil colloids. So let's look on the size. Size is the most important common property of inorganic and organic colloids because they have extremely small size and they are too small to be seen with an ordinary light microscope. They can be seen only with an electron microscope. And most of them are smaller than 2 micrometers in diameter. For the surface area, because of their small size, all soil colloids expose a large external surface per unit mass. And the external surface area of 1 gram of colloidal clay is at least 1,000 times that of 1 gram of coarse sand. And certain silicate clays have extensive internal surfaces as well. And these internal surfaces occur between plate-like crystal units that make up each particle and often greatly exceed the external surface area. And the colloid surface area in the upper 15 centimeters of a hectare of a clay soil could be as high as 700,000 kilometers squared per gram. So that is very large. For the surface charges, the soil colloidal surfaces, both external and internal, characteristically carry negative and or positive charges, but for most soil colloids, electronegative charges predominate. And the magnitude of the charge is known as zeta potential. The presence and intensity of the particle charge influence the attraction and repulsion of the particles towards each other, thereby influencing both the physical and the chemical properties of the soil. And the negative or positive electrical charge in clays comes from isomorphic substitution and hydroxyls and other functional groups. In isomorphous substitution, the charge imbalance that brought about this process in some clay crystal structures create negative or positive electrical charge. The hydroxyls and other functional groups on clay surfaces or of the colloidal particles can create also negative or positive electrical charge. So these charges that can be obtained that is due to hydroxyls and other functional groups are called pH-dependent charges. For isomorphous substitution, for positive charges, the substitution of higher charge ion for lower charge ion create positive charges. For example, aluminum 3 plus for magnesium 2 plus or iron 2 plus. So higher charge, for example 3 plus, substitute for lower charge, we have magnesium 2 plus or iron 2 plus. For negative charges, we have the substitution of lower charged ion for higher charged ion. For example, magnesium 2 plus for aluminum 3 plus or aluminum 3 plus for silicon 4 plus. So as you can see on this diagram, When magnesium 2 plus replaces aluminum 3 plus, it can leave a net negative charge, making the soil negatively charged. Now let's look on hydroxyls on the surfaces of colloidal particles. For positive charges, as soils become more acid, the hydrogen ions attaches to the exposed hydroxyl ion, or can be called protonation. Example, you have aluminum hydroxide when combined with hydrogen ion could produce aluminum hydroxide with a positive charge. For the negative charge, when OH group or hydroxyl group attaches to the iron and or aluminum in the inorganic colloids and to the carbon in the humus, you will have a negative charge. Next is the adsorption of cations. As soil colloids possess negative charge, they attract the ions of an opposite charge to the colloidal surfaces. Now, because our soils have net negative charge, the soils can adsorb on their surfaces the cations, the cations that the plants need. They attract hundreds of positively charged ions or cations such as hydrogen ion, aluminum 3 plus, calcium 2 plus, and magnesium 2 plus. Thus, a colloidal particle is accompanied by a swarm of cations that are adsorbed on the particle surfaces. Next is adsorption of water. A large number of water molecules are associated with soil colloidal particles. Some are attracted to the adsorbed cations, each of which is hydrated. Others are held in the internal surfaces of the colloidal particles. Same as what we have discussed on soil water. And this play a role in the survival of microorganisms, especially bacteria. Next we have is cohesion. Cohesion is a phenomenon of sticking together of colloidal particles that are of similar nature. This tendency is primarily due to the attraction of clay particles for the water molecules held between them. And when colloidal substances are wetted, water first adheres to the particles and then brings about cohesion between the two or more adjacent colloidal particles. Next is adhesion. Adhesion is a phenomenon of colloidal particles sticking to other substances. Sticking of colloidal materials to the surface of any other body or substance with which it comes in contact. We have is the swelling and shrinkage. Some clay or soil colloids, such as smectites, swell when wet and shrink when dry. Was what I've discussed earlier about the Montmorillonite or the 2:1 expanding clay type. After a prolonged dry spell, soils high in smectites often are crisscrossed by white, deep cracks which at first allow rain to penetrate rapidly. When wetted, such soil will swell, close up and become more impervious than one dominated by kaolinite, chlorite, or fine-grained micas. Vermiculite is intermediate in its swelling and shrinking characteristics. The next one we have is the dispersion and flocculation. As long as the colloidal particles remain charged, they repel each other and the suspension remains stable. If on any account they lose or lost their charge, or if the magnitude of the charge is reduced, the particles coalesce, form flocks, or loose aggregates, and settle out. The reverse process of breaking up of flocks into individual particles is known as the flocculation or dispersion. Next we have is the Brownian movement. When a suspension of colloidal particles is examined under a microscope, the particles seem to oscillate, and the oscillation is due to the collision of colloidal particles or molecules with those of the liquid in which they are suspended. And the smaller the particle, the more movement will be. Next is the non-permeability. Colloids, as opposed to crystalloid, are unable to pass through a semi-permeable membrane. Even though the colloidal particles are extremely small, they are bigger than molecules of a crystalloid dissolved in water, and the membrane allows the passage of water and of dissolved substances through its pores, but retains the colloidal particles. So that's all for our topic on soil colloids. I hope you learned a lot. Thanks for watching. Please don't forget to like and subscribe.